now that we know how to read and write voltages to the digital input and output pins on the PIC, let's talk about the circuits and the digital and the physical hardware that we will wire up to these digital input and output pins so that we can detect things like button presses. All right, so our goal is to set the state of an input line to either high or low using a button or a switch. So for example, let's see if we are in draw. Awesome. Okay, so for example, we've got our microcontroller. This is some generic microcontroller with a digital input pin A1, and we've got a physical wire connecting to a 3.3 volt input. And our we would think that, okay, when the switch is open, right here, when that switch is open, we are maybe naively assuming, well, we'll have 0 volts there, right? So that's a question mark. And then when the switch is closed, we will have 3.3 volts, question mark. Okay, so it is true that when the switch is closed, we will have 3.3 volts. But when the switch is open, we will not necessarily have 3.3 volts. We call this a floating voltage, and the voltage is actually unknown when the switch is open. So, just doing it. Oops. Okay, so the question is, how do we avoid a floating voltage? And so when the switch is open, we have to drive the voltage to some value. And so to do that, we use what's called either a pull up or pull down resistor. So let's take a look at the pull up resistor. So when we insert a resistor here and the switch is open, in this case, with this pull up resistor configuration, this pin will be at 3.3 volts. Okay, if this is 3.3 volts. Okay, and then when we close the switch, if this is a very high resistor value, when we close that switch, any voltage will be pulled to ground, and so we will have, when the switch is closed, we will have 0 volts on that line, because the resistance through this leg to the ground is much, much less than the resistance through this leg to the 3.3 volts. Okay, we can do a similar type of configuration, but using what's called a pull-down resistor. So we have a really high resistance value here, and when the switch is open, the value on that digital input pin is 0 volts, and then when the switch is closed, because the resistance of this leg is much, much lower than the resistance of this leg, the voltage will jump from ground to 3.3 volts. So that's how we implement pull up and pull down resistors and avoid a floating resistance value. Let me just remind you that the resistance on an input pin is very high, very high. So the digital input pins have high impedance or high resistance. Okay, so let's take a look at a demo that does that. So we've implemented here a pull-down resistor, and it's a pull-down resistor because when the switch is open, the resistor pulls the voltage down to ground or 0. Okay, so let's look at pin 5 on our PIC, and we'll use that. We're going to configure pin 5 on the PIC to be a digital input, and recall right here, pin 14, we're going to keep as a digital output, so that whenever we press this button, we send a 3.3 volt output on pin 14. So that's our goal. So we build the physical circuit. This is what the circuit looks like. We've got our pull down resistor to ground right here, and then the other side of that switch is connected to a 3.3 volt rail, and then the output of that switch is connected right here to pin 5. Okay, so let's go ahead and take a look at the code that does that. Alrighty. Okay, so back to our code. We've got our preprocessor directive that lets us debug. And again, if we're not going to debug, we can, actually not again, this is the first time I've mentioned this. So if we're not going to use debugging, we can comment out that line, and then we can go over here and we'll clean up and build the main project for non-debugging. And then we can go here and upload the code to our pick, and breakpoints won't make any difference if we're not debugging. So this is how we upload and run code if we're in a non-debugging mode. Recall that we're going to use this if we've built it for debugging. Anyway, so we have our oh, you know what? I should probably set this as our main project, because otherwise we would be still working on our blinking LED project. Okay, button press. Let's go back here. Okay, so we can enable that or disable it. Let's go ahead and disable it for now. So good practice, we clear all of our registers that we will be using, and then we start setting things up. So we're going to be setting up pin 5, which is on port B, and it happens to be the RB1 port bit of pin that's associated with pin 5, and we're going to set that up as an input using our tris-B register. So here is RB0 right there. This is RB1. We're setting RB1 to 1. Remember, 1 looks like I for input. Everything else on port B is set as output. So we're setting up that one pin, pin 5, as input. And then input. And then we jump into our while loop, and we're going to check the voltage on pin 5 using our port B register, and we're going to use the bitwise AND operator. So whatever value is here on port B, if the second, basically if the second least significant bit is 1, that's what this bitwise AND operator does. If then this result of this bitwise AND operation will be 1, which is not 0, which is equivalent to true in C. So basically, if that bit on the port B register is activated, that means there's 3.3 volts on that pin from someone pressing that switch. So we're going to jump into this line of code, and we're going to set the latch for pin 14, just like we did in our LED blink function. We're going to set the latch for that pin high, which turns on the LED. So if the button is pressed, LED turns on. If the button is released, then we go, and then the result of, then everything in the port B register that we're reading will be 0. So this statement in here will, the bitwise AND operation will be 0, which is equivalent to false. So then we'll jump down in here and we set the latch. You know, basically we're just setting all the latch register bits to 0. So that will turn off the LED. So button press, LED turns on. Button released, LED turns off. All right, so the next question is, how do we choose resistance values for these pull up and pull down resistors? Well, let's look at each case. So when the switch is open for our pull up resistor case, we want this R value here to be small enough so that the voltage, drop here, so if we're at 3.3 volts here, the voltage drop keeps us above our voltage high input value for that pin. And so remember, the PIC is looking for a voltage above about 2 points, what was it, like 2.4, 2.6 volts before it interprets that as a high voltage. So if this R value is too high, then the voltage when the switch is open will may be lower than 2.6 volts, and then the PIC won't recognize it as a high voltage. So we want it to be small enough so that that voltage is above 2.6 volts, closer to 3.3 volts. Now when the switch is closed, we want R to be really large because basically current, we don't want a whole bunch of current just flowing directly from our battery to ground. So we have these competing types of requirements. And it turns out that an R value of about 10,000 ohms often works for both, for that case. So it's low enough that the voltage here will be higher than 2.6 volts, and it's high enough that we won't drain a lot of our battery to ground when the button or when the switch is closed and the button is pressed. And that rule kind of works as well for pull down resistors. So when our switch is open on a pull down resistor, we want our R value to be small enough so that the voltage is pulled to ground relatively quickly. If R is really, really high, then that residual voltage on that pin might not get pulled all the way to ground. But we want R large enough to keep the current low when the case for the in the case of the closed switch. So when the switch is closed, we've got all this voltage or current flowing to ground if R is small. So again, 10K works pretty well. So when you're implementing your pull up and pull down resistors, just use a value of 10K. We've got lots of different types of switches. Each of these types can be implemented with pull up or pull down, but these are like physical representations or these are representations of physical switches. So this symbol here is a what's called a single pole, single throw switch. You can have switches like this, which are double pole, single throw switches. So basically they're tied together here. So one mechanical switch action gives you two poles. So this is a pole and this is a pole. Now you can toggle between poles. So this one's called with a single mechanical action. So this is called a single pole double throw switch. And then we've got the double pole double throw switch, and then you have rotary switches, and there are many other types of switches. This is what some of the physical representations of those switches are. These are not these images are not correlated, so not correlated to the schematics above. These are just random switch images. We've got toggle switches, slide switches, rocker switches, push button switches. Those can each be single pole, single throw, or single pole double throw. We've got dip switches. That's more similar to a rotary switch. And then we've got just mechanical snap action type switches. So you just push on this lever arm and it pushes that switch button. All right, so that's physical implementation of switches that then you can interface with the digital inputs on your PIC.